Hello, hello, hello. Okay. So yesterday we see boundaries. What is medium boundaries and boundary relationship? We are going to continue that. Uh, so the four main boundary condition: electric flux density, where rho f is the surface charge density. The the normal component of D equals the surface charge present at the boundary. D2n minus g1n equals to rho s. So so I'm very well, but there is one important correction. What exactly D1 and D2n means? E is electric flux density, not electric charge density. Sorry, yeah, electric flux density. So D1 and normal component of electric flux density in the medium one, D2 and normal component of electric flux density in medium two. So substitute one or two tells you which volume. The n tells you normal to the boundary. So imagine medium. This is medium one, this is medium two. D1 is here, D2 is here. Mm, this is the boundary. So it does not mean D1 and charge density in medium one. It means sorry, how much electrical density points perpendicular to the boundary in medium one. The actual surface charge density is rho s as unit cm itself. Then why are we using a normal component for D? This is the really important part. It comes of density from Gauss law. Uh, let's see what is this at. So we know this. My doubt is why is electric charge. This is electric flux. Sorry. This is electric flux density, then y the d1 and d2 and y it tends to do normal, y not tangent. So that's my dot. So d equals to permittivity, then d1 and equals to normal component of electric flux density in medium 1, d2 equals to normal component of electric flux density in medium 2. The helping 1 or 2 tells the identification of the medium. The n tells the normal to the boundary. The n tells the normal to the boundary. So this is medium and medium 1. This is d2 and medium 1 for electric flux density. The actual surface charge density represented by rho s, surface charge density is represented by rho s. So in the earlier we got d2 minus d1, uh, d2 n minus d1 n equals to rho s surface charge density. To get surface charge density, we subtracted the d2 n electric field density of medium to normal component with the electric field density of the medium one normal component. Um, It's represented with events, but then why are we using the normal component for D? This is really important now. It comes directly from Gauss law. Remember that ds bar is uh, this is a vector quantity ds. This is D. So its points normal or perpendicular to the surface. So electric field is perpendicular to the surface, right? Yeah, perpendicular to the the propagation. So the maybe that's not the reason. This is boundary. Therefore, it points normal for perpendicular to the surface. So when we use a tiny pillbox around the boundary, this is the boundary. Let's say it's the boundary. It's like glass or some mediums. This is air. This is glass. Like yesterday, this was yeah. So this is the boundary. Points normal or perpendicular to the surface. So when we use a tiny pillbox around the boundary, that's a tiny pillbox. The top and bottom surface of pillbox are perpendicular to the boundary. So the open to bottom surface are perpendicular to the boundary. Uh, this surface. The normal component D contributes to the electric to the surfaces, that is the Gauss law. Uh, Gauss law states electric flux contributes uh, the normal component. D contributes the electric flux. D contributes the normal component of D contributes the electric flux to the surfaces, that is the Gauss law gives T2 minus D1 equals. So the equation basically saying if there is surface charge at the boundary, the normal electric flux density can change in crossing the boundary. So to calculate the surface charge across the boundary, on the boundary we have two electric fluxes. We can calculate it by d2n minus d1n. So we'll get the boundary surface charge. And y tangential h. Now we use a different Maxwell equation. Here, y for magnetic fields we use the tangential tangential component. This is Ampere's law. Here, dl is along the path. So we use a tiny rectangular loop lying around the boundary. So this is the boundary. A tiny rectangular loop is here. The two long sides of the loop are perpendicular to the boundary. The two loops are perpendicular to the boundary. Therefore, the component of H that contributes is its tangential component. That's why we get N minus H2 minus H1 equals to Gs. Gs is current. This is the magnetic field's attraction. So when there is no surface current, H1T equals to H2T. If there is no surface current, then H1 goes with this side and H1T becomes H2T. So your question has deeper answer. Why did he use only normal component for expressing tangential component magnetic? It's not because electric wheels only have normal component, magnetic wheels only have tangential component. There's a solution to think. Both can have normal and tangent component. We choose the component according to which Maxwell equation we use. Gauss law normal component. This is charged. The divergence of natural and Gauss surface is area vector is normal dm and face the tangential component here. Magnetic field. Here the electric field creates magnetic field called naturally involves circular magnetic loop their history. Maxwell Gauss law for me Gauss law the Gauss law. D is normal and the H is angle does not current D. Gauss law is normal for, for circulation of current means tangential. Because you, Gauss law itself is normal time, normal component. And Fifth law when it's a circulation of current it's tangential. Explain dx and prove how it will be Darby. As this is the right place to slow down because ds and dl are the reason we get normal time boundary condition. Let's build some geometry rather than memorizing formulas. First, what are ds and dl? There are two completely different mathematical objects dl, a tiny length along a path. Imagine walking along a curved path. At every tiny piece of path, there is a tiny displacement dl. So, tiny length along a path. Dl means imagine walking around a curved path. This is a curved path. We are walking along it. At every tiny piece of path, there is a tiny displacement below. It points along the path. If you are moving horizontally, dl is horizontal. If you are moving vertically, so if you move horizontally, like this line, sorry, this line horizontally, then dl is horizontal. If you move vertically, then dl is vertical. So dl tiny vector along a line or path. ds. Now forget the line. Think about a tiny surface or area. Imagine a tiny patch of a table ds. The area itself lies horizontally, but ds is defined to point perpendicular to the surface. So imagine a tiny patch of a table. This is well, let's imagine a table. It's tiny patch on it. Patch means a small damaged area. Now forget the line. Tiny surface area. Now this is a small patch or it in like something imagine. The area itself lies horizontally. So the area is lying horizontal, it's not vertical. The table's top is horizontal, right? This is horizontal surface. It's a tiny patch, but ds is defined for a point perpendicular to the surface. So the surface is different, but it is defined to be perpendicular to the surface. Therefore, ds equals to n ds. So where ds equals to tiny scalar area, this is a scalar area, means it has no direction. But we added a normal, so unit vector normal to the surface. So it is has a direction perpendicular to the surface. It is horizontal to the surface, but we need it perpendicular to the surface. We add a unit vector normal to the surface. So ds is an area vector, not a little arrow lying around along the surface. So, but why does the area vector point normal? This is an arbitrary electromagnetic rule. It's built into the definition of flux to a surface. Suppose wind is blowing toward the window. Suppose wind is blowing toward a window. Wind strikes into the window. Maximum amount of wind passes through the window and expands this to the phi equals to F dot S bar force into S bar area. The area vector points perpendicular to the window. Turn the window sideways, and almost none of the wind passes through the window. The flux object is mathematically F is cos theta, where theta is the angle between the field and normal to surface. That's why the surface direction is represented by its normal. Now let's connect to the electric flux. Electric flux is this is phi equals to E vector equality and ds. The dot product gives E ds cos theta. But what does E cos theta represent? It exactly the component of E perpendicular to the surface. Therefore, E ds equals to E and ds. E cos theta represents ds. That's the fundamental reason normal components appear in Gauss law. It's not a coincidence. Mathematics. Here to vector count theta T and ds. If we do integral, the dot product gives E inverse cos theta. What does E cos theta represent? It exactly component of perpendicular to the surface. E perpendicular to the surface. E cos theta represents the electric field perpendicular to the surface ds. S means surface. So that's the normal appears in the Gauss law. Then let's derive dm boundary condition. Top ds, bottom ds, perpendicular right, one upward, one downward. Because this is boundary, we think it as a patch or this is a patch. These are normals to the sides. So then what about the side? This is extremely important on the side of the because ds point sideways. Suppose the boundary is horizontally, ds if the field of perpendicular infinitesimally thin its side area goes to zero, therefore side flux is zero. The side flux is zero. Only the top and bottom contribute surface, so d2 and minus d1 ds equal to q. We know q by like this is charge unit. The surface charge density is definitely is q by ds. So by math we get d2 and minus d1 and equals to ρs. And now you can see why exactly why dn appears. So why it becomes is a bulbous becomes infinitesimally thin. Its side area goes to zero. Therefore, uh, pillbox. The viewers are calling this as pillbox. If it is extremely thin, its sides are equal to zero. Then side flux is zero. We will only have a top and bottom flux. Uh, Same do with the now. Let's go into the magnetic field dm. The Ampere's law. We don't take a separate integral. We take a line integral. Walking around a closed path. Imagine a rectangular loop dl. This is a closed path. We are walking like this. Notice something dl lies along the loop. Therefore, the field component that contributes to h dot dl is the component of h parallel to the loop. Uh, Here, the field component that contributes to magnetic field and the dl is a closed path is the component of h parallel to the loop. It is parallel to the loop. Magnetic field is parallel to the loop. That's the tangential component. Why does the boundary conditions use tangential rays? It's not tiny rectangular loop around the boundary. Rectangular loop, this is a rectangular loop. The top sides, sorry, the top side is slice medium 1, the bottom side is medium 2, both are parallel to the boundary. Both are parallel, therefore, the DL are parallel to the boundary. If you are DL, H2 minus H1 is H2T DL. Okay, this is vector quantity and normals of this is GS. Normal. This is normal. Vertical sets become infinitely short. So in the previous one, we get this horizontal. Okay, the vertical sets become short. So the contribution value is H1 to DL and H2 to DL is JS divided in the form. This is normal. This is normal. Normal H2 minus H1 into JS. In normal way, you can just derive this. But this is the first tangential. Here the deeper geometry, you can actually derive the whole pattern for one simple surface integral as how much of the field is going to the surface, therefore we need the components perpendicular to the surface. Surface integral means a normal component line integral as how much of the field is pointing along the path. Therefore we need the component parallel to the path, line integral means tangential component. Here electric field, it is asking how much field is going to the surface. When it is asking going to the surface, we can say the component is, therefore we need the component parallel to the surface, then surface integral is normal component. When it is say going to the surface, we can say normal component. When it says field is pointing along the path, it is parallel to the surface. Going to means it is perpendicular. Pointing along means it is parallel. So then line integral with tangential component, which extends all four electromagnetic boundary conditions. Gauss law for D D dot ds plus v. So this is derivations happen from last. We have been seeing it from before and after. So we know why it comes, why this comes. If it is current is zero, then H2 is let's see. We get both. Yeah, here. He said altitude is V1 plus V2 magnetic is Hn minus V. We divide it as normal and tangent component. So D2 and we derived this where D equals to epsilon naught, we can turn this into. For a charge density, the jump in normal component B equals to surface charge present at the boundary. If there is no surface charge, then D1 equals to D2 D equals to permittivity V, permittivity 1 9, E1 9 equals to V, permittivity 2 into F. Altitude D, the tangential of the field is continuous, E1 equals to E2T, tangential of the field equals to tangential of the field 2 of medium 2. If there is no electric field, okay, then if this happens, D1 equals D2N, then electric field, the tangential for electric field is continuous, D1 equals to E2N. Under the usual electrostatic action boundary condition situation requires simplify varying magnetic flux to the infinitesimal. Note this one is very important for just magnetic flux density B or Gauss law for magnetic gas. This is del dot B equals to 0, which gives D1 and equals to D2N. For a closed path, there are no, we derive this in previous equations. For there are no monopoles, so it forms closed path, so the net flux equals to 0. Flux net magnetic flux equals to 0 because it has no change. Um, there are no magnetic monopoles, so the normal component B cannot suddenly jump since B equals to mu H. You can say mu1 H1 equals to mu2 H2. And here it is permittivity E1 and this is permittivity, this is permeability mu1, mu2. Magnetic field H. So from Ampere's Maxwell's law, del curl H equals to J plus partial derivative of D. The tangential component satisfy this. we derived this. Gs is the surface current density. So OS we discussed earlier is surface charge density. This is surface current density. If there is no surface current, H1 equals to H2. Here if there is no surface flux, E1 equals to E2. Here if there is no surface flux, H1 surface current H1 equals to H2. The easiest way to remember, make the table a mental model. So this is our mental model. Depends on D and the surface charge density, E1 equals to E2T. For electric fields, for my electric flux, D2 and given equals to surface charge density. For normal component, B1 n equals to B2n. It is always B1 n equals to B2n because net magnetic field for a magnetic field values into the surface is equal to 0. H equals to depends on the magnetic field depends on the jump depends on the S. Electric surface current density E1 equals to B2. The two cleanest fundamentals are the B1 n equals to B2 and according to the standard case. Why do we care about normal versus tangent? This is where boundary becomes institution. Imagine a flat boundary. This is a flat boundary. This is normal component is perpendicular to the boundary. Tangential component is parallel to the boundary. Here normal component crosses the boundary, crossing the boundary. Normal component vertical. The tangential component runs along the boundary. It is running along the boundary. Different Maxwell equations control these two behaviors. That's why we don't simply electric field and continuous. Different components behave differently. One very important special case is conductor. For a perfect conductor in electrical electrostatic equilibrium, A inside equals to 0. Therefore, at the conductor surface, tangential electric field is equals to 0. Otherwise, charges would move along the conductor. Electric field is perpendicular to the surface, so just outside the conductor, this is vector E equals to E1 normal and Bn equals to OS. Therefore, electric field just outside a conductor is perpendicular to its surface. Its magnetic field is determined by the surface charge density. This is very common exam concept. So we'll stop here. We'll continue.